Hi, I'm Mariah Etheridge, and today I will be presenting my neural network image classifier final project. So I did the fashion MNIST neural network classifier. This network classifier predicts clothing and accessory categories from grayscale images. I chose this because it's a well-balanced data set, it has real-world application, and it's a manageable size for training. The real-world use cases, or how you can use this in the real world, is automated clothing categorization for e-commerce, inventory management systems, fashion recommendation engines, and quality control in garment manufacturing. So the dataset is the Fashion MNIST. The source is from Zalando Research. I've included the link. It's built into the Keras dataset. The statistics are that there's 70,000 total images, 60,000 for training, and 10,000 for testing. There are 10 classes of clothing items. The format is 28 by 28 grayscale. The pixel values range from 0 to 255, normalized to 0 to 1, like we learned in class. And the classes are t-shirt top, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, and ankle boot. For the data overview, here are some sample images. I've included the trousers, a t-shirt top, bag, ankle boot, pullover, and a coat. Here is my neural network architecture diagram. Shows you the different layers and then a little bit of information on each layer. And then to go more into that, for the input layer, we have flattened 784 neurons. It converts 28 by 28 images to a 1D array. For the hidden layer, we have it, the categorization is dense, 128 neurons, ReLU, and then it learns low-level features. For the hidden layer 2, similar deal, it's dense, 64 neurons, ReLU, but it learns high-level patterns. And then for the output layer, dense, 10 neurons, use softmax, and then produces class probabilities. The total parameters are 109,386. And to break that down a little bit more, layer 1 gets 100,480 parameters, layer 2 gets 8,256, and layer 3 gets 650. For the model training, for the pre-processing section of it, it normalized pixel values 0 to 1 range. There was no data augmentation, and the training / validation split was 80-20. And then for the training configuration for epochs, there's 10. The batch size is 32. Optimizer is Atom. The loss function, sparse categorical cross entropy, and then hardware CPU / GPU. Performance metrics, training accuracy was 89 and 91%. I've included some photos from when you run the code, what gets outputted at the bottom. Validation accuracy 87 to 89%. Test accuracy was around 87 to 89%, and then test loss was roughly 0.35 to 0.40. More results. Here's one of the images that gets output when you run the code. My interpretation of this is that the model does learn effectively without significant overfitting. Validation and test accuracies are close, which is a good indicator of good generalization. And then there is a small gap between training and validation, but that shows the model isn't memorizing, it's acting as it's run. Here's some of the, here are the 10 outputs for the epochs for predictions, and then for more predictions, I just included 10 sample images that get output when you run the code. My observations about this are that the model performs well on distinct categories such as sneakers, bags, and trousers. There is occasional confusion between similar items like shirts versus t-shirts or pullover versus a coat. But the confidence scores are typically high for correct predictions. And reflection, what did I learn from this? What was difficult? So understanding parameter calculations was initially a little difficult for me. Choosing appropriate layer sizes in architecture and balancing model complexity versus training time. Overall, the project, it was smooth sailing, but those are some of the things that I think are my weaknesses with this project. And then as far as what was surprising, I was surprised at how well a simple architecture performs. It was roughly 88% accuracy, which is just interesting. The speed of training on Fashion MNIST, it was pretty quick. And then the clear visualization of learning curves showing convergence. And then as far as improvements, I think I could add convolutional layers for better feature extraction, data augmentation such as rotation, zoom, shifts for better training, dropout layers to reduce overfitting, probably experiment with different architectures such as like more layers or just different neuron counts, and then hyperparameter tuning such as like learning rate and batch size. That is all I have for this presentation. Thank you.